Hello everyone, I'm Milind Prabhu from the University of Michigan. Today I'll be talking about sensitivity sampling for k-means, worst case and stability optimal Coreset bounds. This is joint work with my wonderful collaborators, Nikhil, Vincent, David and Chris. The overall theme of this talk will be clustering algorithms. Specifically, we are interested in Euclidean k-means clustering. Let me quickly recall what this problem is. So in this problem, you're given a set of points P, which lie in d-dimensional Euclidean space. And you're also given an integer k. And the goal is to output k centers which minimize this objective. In this objective, you have the sum over all points P of the squared norm of P to the nearest center in S. So the goal is to figure out these k centers which minimize this objective. To make notation concise, I'll use cost of P to S to denote the squared distance of P to the nearest center in S. Note that once the centers are given, these naturally induce k clusters obtained by taking every center ai and looking at all the points in P which is nearest to ai. Now let me define what a clustering coreset is. So a clustering coreset is a small weighted subset of the original points which preserves clustering structure. So exactly what this means, to explain this I'll need some more definitions. So let's say P is this set of input points. A coreset would look something like this. It's a subset of these points and each point has a weight. And we'll use omega to denote these weighted subset of points. Now let's say S is a set of centers. The cost of the coreset is defined as just the weighted cost of these points. Now, a set of points is called a coreset if it satisfies the following guarantee, that for any placement of these centers S, the cost of the coreset, cost of omega S, is approximately equal to the cost of the input set of points P. In other words, these small weighted subset of points provide a good approximation for the cost of any set of centers S. More formally, a weighted subset omega of the points input points P is an k epsilon coreset if for every set of k centers S, the coreset cost is a 1 plus minus epsilon approximation to the true cost. And I would like to emphasize that this guarantee must hold simultaneously for all placements of these k centers S. So now that I've defined what a k epsilon coreset is, let me try to spell out what the goal is of this talk. The goal is to come up with a k epsilon coreset constructing algorithm which produces coresets of small size. And by size, I mean the number of distinct points in the coreset. And ideally, we would like our algorithms to be fast and also simple. And such an algorithm has lots of applications. In particular, coresets are widely used as a pre-processing step in fast algorithms. Also, these are very useful primitives in distributed computing and streaming algorithms where the memory is constrained. Also, these are useful for dynamic algorithms for clustering. Also, the existence of small coresets is a very useful mathematical fact when you want to analyze certain problems. Now, before I go into our work on coresets, let me try to sketch out the previous work on the sizes of Euclidean coresets. The coreset problem was first proposed by Harpeleth-Mazumdar in STOCK 2004. And over the last 20 years, there have been several results which have improved the size of these coresets. The first result by Harpeleth and Mazumdar was the following bound. Note that the coreset size will depend on these four parameters: n, which is the number of points, d, which is the dimension, k, which is the number of centers, and epsilon, which is the precision parameter. The bound of Harpeleth and Mazumdar was the following: k epsilon to the minus d plus 2 times log n. Note that the dependence on dimension is exponential in this bound. Chen showed that you can in fact improve this to dk square epsilon to the minus 2 log n. So you can actually get a linear dependence of the dimension. Feldman and Langberg further showed that the dependence on n is unnecessary. So you can get a bound which is only dependent on dk and epsilon. And after a sequence of many works, Zoller and Woodruff showed that you can indeed get a you can in fact get a polynomial in k over epsilon bound, which is a huge development because now you don't even need the dependence of the dimension. And after many intermediate results, we have this bound, which pins down the exact polynomial in k and 1 over epsilon, which is achievable. So Cohen-Addad, Larson, Saulpic, Schwiegelshohn, Shea-Comer showed that there's an algorithm which is called group sampling, which obtains a coset of size k epsilon to the minus 4, minimum of k epsilon to the minus 4, and k to the 1.5 times epsilon to the minus 2. So this is the upper bound we know. This is just, I just copied it from the previous slide. And as for lower bounds, Cohen-Addad, Larson, Saulpic, and Schwiegelshohn showed that there is a k epsilon to the minus 2 lower bound. And since it looks very natural for our problem, they even conjectured that this might be optimal. Surprisingly, it was shown in Stock 2024 by Huang, Li, and Wu that this is not the case, that you can show a stronger lower bound of k epsilon to the minus 4. And if you check these bounds, what you'll see is that this shows that the group sampling algorithm is optimal for some ranges of k and epsilon. So this is a very cool result. So now you might think, well, group sampling is already optimal, so what is there to study about this problem? But the thing about the group sampling algorithm is it is optimal, but it is quite cumbersome and there's a lot of case work. And so one would hope for a cleaner and simpler algorithm, which is also optimal. And empirically, it was observed that there is this very simple algorithm, which is called sensitivity sampling, which did very well. So this was observed by in an ESA paper by Schwiegelshohn and Shea-Comer. And they observed that sensitivity sampling always outperforms group sampling. However, it was unclear if sensitivity sampling was provably optimal. There's a previous result by Huang and Bishnoi who studied some variant of sensitivity sampling, which gives this k epsilon to the minus 6, minimum of k epsilon to the minus 6 and k square epsilon to the minus 4 bound. But this is not, this is worse than the bound we know for group sampling. So our main contributions are showing, our first main contribution is showing that sensitivity sampling is optimal, and it has size minimum of k epsilon to the minus 4, comma k8 to the 1.5 epsilon to the minus 2. And this matches the size of group sampling. So, and this is also optimal for that reason. So what we have is a very simple and practical optimal Coreset algorithm. And just to indicate how simple this algorithm is, it can be written in 3 lines. So I won't go into the exact details of the algorithm, but roughly speaking, the first step just computes an approximate k-mean solution. The second step uses this solution to define a distribution over the input points, and the third step just samples points from the distribution defined in step 2. So just these 3 simple steps gives you like an optimal Coreset. So this was our first contribution. Our second contribution involves a beyond worst case analysis for Coresets. So real world inputs are reasonable and they do not have pathological structure. So it is reasonable, it is probably reasonable to imagine that smaller Coresets might be achievable since they have like meaningful clustering structure. So just to give an example of what this means, so if you look at the figure on the left, it has a meaningful 3 clustering because it's visually clear that there are 3 distinct clusters, whereas on the right there is no meaningful clustering. And so in the real world, when we are looking for a K clustering, we sort of know that there are K clusters. So to formalize this, many definitions have been proposed by previous work to formalize this notion of what is a meaningful clustering. And we looked at this definition called cost stability due to Ostrovsky, Rabbani, Schulman, and Swamy. So let me quickly define this. So let opt k denote the cost of the optimal k clustering of these points. So notice that the optimal cost with respect to k minus 1 centers is always going to be at least as large as the optimal cost with respect to k centers. An input is said to be beta cost stable if the optimal cost of k minus 1 is significantly larger than the cost of the optimal cost with respect to k centers. In particular, if opt k minus 1 is at least 1 plus beta times opt k, then we say the input is beta stable. So this is the notion of cost stability. And in the picture above, let us see why this definition sort of tells us that the left input is cost stable, whereas the right input is not. So firstly, let's look at the clustering with just 2 centers. These are the yellow centers. And let's compare it to the cost with respect to these blue centers. Clearly, like the cost with respect to the 2 centers is significantly larger because the cluster has just like, it looks like it has 3 clusters. Whereas on the right hand side, the optimal cost with respect to 2 centers and the optimal cost with respect to 3 centers are quite similar. So this is roughly why the left figure is cost stable, whereas the right figure is not. What we show in our paper is that when the inputs are constant cost stable, we can indeed obtain coresets of size which have size better than like worst case coreset sizes. So we can obtain a coreset of size k epsilon to the minus 2. This beats the worst case lower bound of k epsilon to the minus 4. And what's even cooler is that this can be obtained by exactly the same algorithm as before. We just use sensitivity sampling and sample a fewer number of points, just k epsilon to the minus 2 points, and we can obtain a k epsilon coreset. And we show that this result is in fact tight, that there exists inputs for which we really need k epsilon to the minus 2 size coresets. I now give a sketch of some of the ideas, and I will also motivate sensitivity sampling. So let's look at a first attempt at constructing coresets, which is uniform sampling. So the algorithm simply samples m points uniformly from the input points and assigns equal weight of n over m to each sampled point. And the question is how many points are required for this to be a good coreset. I claim that there exist instances where you need to sample a linear number of points for this to be any good. So consider the following example where there are 2 groups of points. The left group of points contains a total of n minus 1 different points, and the other group contains only 1 point and is very far away from these n minus 1 points. I claim that in this case, any good coreset must pick the point on the right. So let's see why. Suppose the coreset did not pick the point on the right and only picked points from the left. So let's say these are the red points are the coreset points. And then what the adversary can do is the adversary can place a single center close to the red points so that the true cost is d squared and is contributed to entirely by the point on the right, whereas the coreset cost is close to 0. So this example shows that we must pick the point on the right, and the only way uniform sampling picks this point is if it picks a linear number of points. The key takeaway is that some points are more important than others and that our algorithm must be sensitive to this information. So how do you identify these important points? And the idea is simply this. So the importance of a point Q in a solution, in a fixed solution S, is given by the relative cost of that point. So the relative cost is the cost of that point in the solution divided by the total cost of the solution S. And this is a very good measure of importance because it tells you how much the point is contributing to the solution. And in the previous example, where there were n minus 1 points in the left cluster and 1 point on the right cluster, we see that the relative cost of the points on the left is about 0, whereas the relative cost of the point on the right is 1. So now this motivates the definition of sensitivity, because we don't care just about a fixed set of centers S, but all possible centers S. So for a point Q, we define its sensitivity score sigma of Q to be the max over all placements of K centers of the cost of Q to S divided by the cost of P to S. And sensitivity sampling simply does the following. You define a distribution over points where the probability of picking a point is proportional to its sensitivity score. And then you independently sample m points, Q1, Q2, Qm, from this distribution. And you do this independently. And to each sample point, you assign a weight so that the estimator is unbiased. One issue with this algorithm is that sensitivity scores are difficult to compute efficiently. However, it is easy to approximate sensitivity scores from a constant factor approximate k-mean solution. And we will be analyzing a version of sensitivity sampling which uses these approximate scores. We will now analyze a version of sensitivity sampling, which I'll now call approximate sensitivity sampling. So this is the algorithm which we look at in our paper. So the algorithm has 3 steps. In the first step, it computes an approximate k-mean solution, A1, A2 up to AK. And then it uses this solution to define a distribution over the input points. And finally, in the third step, it samples m points independently from this distribution, which was defined in step 2. And it also assigns the weight so that the estimator is unbiased. So let me just comment about the distribution over points, because that's the important part. So in words, like the distribution has like 4 different terms which tell you what the probability of sampling a point P is. In words, what these terms say is the following. A point is more important if it lies in a small cluster, a cluster with very few points, or if it has a high cost in this solution that we computed, or if its cost is high relative to the other points in the cluster, or finally if its cluster itself has a high average cost. So it's not clear if this is the simplest form of sensitivity sampling that works, but this is the algorithm which we'll be considering in the paper. So it's potentially possible that some of these terms are not necessary. So finally, this is the theorem which we'll be proving about the algorithm. We show that sensitivity sampling yields a coreset of size which is given in the figure. This matches the size achieved by group sampling and is also optimal for some ranges of k and epsilon. In this talk, I'll be giving a quick sketch for a toy input. This gives a flavor of the argument, but there are many simplifications which we make, which we'll have to handle to give the full result. So let's consider the following toy example, where there are n points which are placed symmetrically on a d-dimensional unit sphere. Now, in this particular case, since all points are symmetric, they are equally important, and sensitivity sampling reduces to uniform sampling. And we'll be showing that uniform sampling gives a k epsilon coreset for this input of size k epsilon to the -2. So again, recall what we have to show is that for any placement of these centers S, the cost of the coreset is a 1 plus minus epsilon approximation to the true cost. First, we make some observations. I claim that if the centers are all far away from the input, then the cost is easy to approximate. So for example, suppose the centers are at distance larger than 1 over epsilon from the origin, as in the figure. In this case, the reason this is easy is because the cost of any 2 input points is similar. That is, for any 2 Q1 and Q2 in the input points, the cost of Q1 to S is a 1 plus minus epsilon approximation of the cost of Q2 to S. So as long as the coreset preserves the number of points in the input, the total cost is well preserved for all such centers which are far away from the origin. So we can assume without loss of generality that all the k centers are within distance 1 over epsilon from the origin. And this will be the challenging case of the proof. So now let's go over the analysis of the closed centers. First, note that the coreset is unbiased, just because of how we assigned the weights and how we did the sampling. And next, notice that by a Chernoff bound, this argument I'll not entirely go through, but what you can show using Chernoff bounds is that if the core set has size 1 over epsilon squared times log 1 over delta, then for any fixed S, the cost of the core set is 1 plus minus epsilon approximation of the true cost, with probability at least 1 minus delta. Now, suppose we want to approximate T different center placements. Then what we can do is we can use a Chernoff plus union bound argument to show that the core set, a core set of size 1 over epsilon squared log delta, log T, approximates the cost of all these T placements of centers with constant probability. However, we care about infinitely many placements of these centers S. So a natural thing we can do is discretize the placements of centers S. And what I mean by this is the following. Consider the figure. Here we have two different placements of centers, the blue centers and the red centers. And these are very close to each other. Therefore, if the core set does a good job approximating the cost of the red centers, then it will also do a good job approximating the cost of the blue centers. So the idea will be to find a finite set of center placements that approximates all possible center placements. And this is what we'll call a net for center placements. So now let me tell you how exactly we'll be I'll give you a sketch of how we'll be discretizing the center placements. This is not exactly how we do it, but this gives you a rough intuition of how this argument goes. I've claimed that it is enough to consider e to the kd different center placements, where k is the k from k means and d is the dimension of the points. So to see why, let me give you some intuition. Consider the unit sphere with radius, unit sphere with radius 1. How many balls are necessary to cover this unit sphere? Balls of radius alpha. By standard argument, you can show that this number is c over alpha to the d. And this is roughly because a ball of radius alpha has volume proportional to alpha to the d, and therefore you'll need about 1 over alpha to the d many balls to cover this unit sphere. And to cover a ball of radius 1 over epsilon, you will need c over alpha to the d times 1 over epsilon to the d, which is c over epsilon alpha to the d. And roughly speaking, this is the number of ways to place a single center within this ball of radius 1 over epsilon. But we care to place k different centers. So the number of ways to place k different centers is c over epsilon alpha to the kd. And this is why we get this exponential in kd different center placements. Now, using dimensionality reduction ideas, one can show that d can be set to 1 over epsilon squared, approximately speaking. And therefore, we only need to consider order of exponential of k times epsilon to the -2 different center placements. Using the Chernoff plus union bound idea, what we can now get is that the core set size needs to be k epsilon to the -4. But what we promised was a core set of size k epsilon to the -2. The final step requires a very powerful tool, which is called chaining. In particular, we'll be using a tool called Dudley's inequality. I'll not go into the specifics of what this allows us, but what we can get is we can get this bound from k epsilon to the -4 to k epsilon to the -2. The key idea is that discretization of centers at different scales can be combined in a clever way to do a better union bound. This is quite vague, but this is a very nice idea, and this allows us to get this improvement in the bound. This is a very magical idea, and it was developed by Kolmogorov, Dudley, Fernique, and Talleyrand. And it is widely used in the analysis of extrema of Gaussian processes. And there have been many recent applications of this idea in theory. So that was a sketch of the proof of the toy example. Now let me briefly comment on the proof of the general case. So the general case follows a similar sort of idea, but it has more steps because the inputs are not as symmetric as we looked at. So the analysis involves the following 4 steps to analyze the closed centers. In particular, we'll first use a tool called symmetrization, which reduces the analysis of reduces showing that omega is a core set to bounding a certain Gaussian process. And then we'll construct nets to discretize the various center placements. And the details are slightly more complicated, again, because the input instances might not be very symmetric. Finally, we use chaining to combine the nets using Dudley's inequality. And this together gives us that sensitivity sampling is optimal in the worst case. And also we can do chaining in a slightly cleverer way for stable inputs to show that under the assumption of cost stability, we get smaller corsets. So this was the end of my talk. In conclusion, we established a stronger bridge between the theory and practice of corsets. We showed that a simple algorithm is optimal in the worst case, and that the same algorithm yields smaller corsets when the inputs are stable. Thank you so much for watching.